Tonight, we're going to confront the most disturbing question in all of science. A question so simple that a child can ask it, so profound that the greatest minds of the last century have never answered it, and so unsettling that the more carefully you think about it, the harder it becomes to sleep. Where is everybody? The universe is 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies. Our own galaxy alone contains somewhere between 100 billion and 400 billion stars. Astronomers now know that most of those stars have planets. A significant fraction of those planets orbit at distances where liquid water could exist on the surface. The chemical building blocks of life, amino acids, complex organic molecules, have been detected in interstellar space, in meteorites, in the atmospheres of distant worlds. Life on Earth began almost as soon as conditions allowed, roughly 3.8 billion years ago, suggesting the transition from chemistry to biology is not impossibly rare, and some fraction of all that life, over the course of 13.8 billion years, should have developed intelligence, technology, and the capacity for spacefaring civilization. So where are they? Why is the universe silent? Why has no confirmed signal from another civilization ever been detected? Why have no alien probes visited our solar system? Why, in 13.8 billion years of cosmic history, is there not a single unambiguous sign that we share this universe with anyone else? This is the Fermi Paradox, named for the Italian-American physicist Enrico Fermi, who reportedly asked at a Los Alamos lunch in 1950, in the middle of a conversation about extraterrestrial intelligence, simply, "But where are they?" The question was casual. The implication was not. If advanced civilization are likely and the universe is ancient, and even modest interstellar travel would allow a civilization to spread across an entire galaxy in 10 to 100 million years, a blink of cosmic time, then the galaxy should already be full. It should be obvious. Silence should be impossible, and yet silence. By the end of tonight, you're going to understand why the Fermi Paradox is not a trivially answered question, but one of the deepest unsolved problems in science. You're going to learn what the Drake equation actually says and what it gets spectacularly wrong. You're going to confront the proposed solutions to the paradox, each of which is more disturbing than the last. You're going to discover why the great filter hypothesis might be the most terrifying idea in science, and why finding life on Mars would be one of the worst things that could ever happen to humanity. And you're going to understand why our own silence, our own failure to have become a galaxy-spanning civilization yet, might be the most important clue of all. Before we get started, if you love exploring the deepest questions about our place in the cosmos as much as we do, take a second to like the video or subscribe. It costs nothing, but it genuinely matters. Now, let's begin. The year is 1950. Enrico Fermi is eating lunch at Los Alamos National Laboratory in New Mexico. He is, at this point, one of the most celebrated physicists in the world. He led the team that built the first nuclear reactor under the bleachers of a football stadium in Chicago in 1942. He was a central figure in the Manhattan Project. He is the kind of scientist whose instincts and rough calculations, which his colleagues called Fermi estimates, are considered a model of rigorous thinking under uncertainty. The conversation at the table has turned to a recent New Yorker cartoon about flying saucers, and then to the broader topic of extraterrestrial life. There is laughter, there is speculation, and then Fermi pauses and asks his simple question, "But where are they?" What Fermi was pointing to with that question was a contradiction. If advanced civilizations are possible, and if the galaxy is old enough for them to have spread across it, then the galaxy should already be colonized, or at least contacted. The absence of evidence should itself be startling. The universe should not be silent, and yet it is. Fermi did not publish this thought. He did not develop it into a paper. The observation was reported second-hand years later by colleagues who were at the lunch. The calculation Fermi may have sketched out informally was never written down, but the question stuck. because it is the kind of question that, once asked, refuses to go away. The astronomer Michael Hart gave the first serious systematic treatment of the paradox. In a 1975 paper, Hart pointed out that even with conservative assumptions about interstellar travel, a civilization with technology slightly beyond ours could colonize the entire Milky Way galaxy in somewhere between 5 million and 50 million years. 5 million years is roughly the time since our ancestors diverged from chimpanzees. 50 million years is roughly the time since the extinction of the non-avian dinosaurs. These are enormous spans of time. From a human perspective, they are tiny compared to the age of the galaxy, which is roughly 13.6 billion years old. If any civilization arose in our galaxy more than 100 million years ago and developed spacefaring capability, it has had ample time to be everywhere. And the galaxy is full of stars that formed 5 billion, 7 billion, 10 billion years ago. Civilization that arose on planets around those ancient stars would have had cosmically vast head starts. The paradox is not that we have not yet made contact. It is that the galaxy should already be saturated, and it isn't, or at least if it is, we cannot detect it. Before engaging with the proposed solutions, we need to understand the mathematical framework that makes the problem quantitative. In 1961, the radio astronomer Frank Drake proposed what became known as the Drake equation. It was not designed as a calculation with a definite answer. It was designed as a framework to organize ignorance, to lay out the factors that need to be estimated before anyone can say how many communicating civilizations might exist in the galaxy right now. The Drake equation multiplies together 7 factors: the rate at which stars form in the galaxy, the fraction of those stars that have planets, the average number of planets per star that could support life, the fraction of those planets where life actually arises, the fraction of planets with life where intelligence develops, the fraction of intelligent species that develop technology capable of interstellar communication, and the average length of time such civilizations remain detectable. Multiply all 7 factors together and you get N, the estimated number of communicating civilizations in the Milky Way at any given moment. When Drake and his colleagues estimated these factors in 1961, with the knowledge available then, they got estimates ranging from a handful to several thousand civilizations in our galaxy alone. These estimates were speculative. The astronomical factors, star formation rates, and planetary occurrence were poorly known. The biological factors were almost entirely guessed. The sociological factor, how long civilizations remained detectable, was pure speculation. 60 years of science have dramatically improved our knowledge of some of these factors. We now know from the Kepler Space Telescope and ground-based surveys that planets are extraordinarily common. Roughly every star in the galaxy has planets. Planets in what astronomers call the habitable zone, the range of distances where liquid water could exist at the surface, are also common. The nearest star to the Sun, Proxima Centauri, has a planet in its habitable zone. The nearest Sun-like star, Alpha Centauri, may have one. We know that complex organic chemistry is ubiquitous. The building blocks of life have been found in meteorites that fell to Earth, in the gas clouds between stars, in protoplanetary disks around newly forming stars. The raw materials of biology are everywhere. We know that life on Earth began astonishingly quickly by geological standards. The planet formed 4.5 billion years ago. The oceans formed perhaps 4.4 billion years ago, and by 3.8 billion years ago, possibly earlier, life existed, given that the late heavy bombardment of asteroids and comets was still ongoing during this period, making the early Earth an extraordinarily hostile environment. The rapidity of life's emergence suggests that the transition from chemistry to biology may not require rare, exceptional circumstances. What we do not know, and what constitutes the deepest uncertainty in the Drake equation, is the factor that biologists and philosophers find most daunting. How often does intelligence arise from life, and how long do technological civilizations survive? We have exactly one data point for both of these questions: Earth, and you cannot make reliable statistics from a sample size of one. The proposed solutions to the Fermi Paradox divide into two broad families. Either they are out there, but we cannot detect them, or they are not out there at all, at least not in any form we would recognize. Let's work through the most serious proposal, because each one reveals something important about what the silence might mean. Solution number one: the distances are too great. Interstellar travel and communication are far harder than we imagine, and civilizations simply cannot or do not make the journey. This is the most comforting resolution to the paradox, and also, on careful examination, one of the weakest. The objection to it is not that interstellar travel is easy. It is obviously extraordinarily difficult by any current human standard. The nearest star, Proxima Centauri, is 4.24 light-years away. At the speed of the fastest spacecraft we have ever built, roughly 40,000 miles per hour, the journey would take about 70,000 years. But the paradox is not about individual journeys. It is about exponential expansion, a civilization that can achieve even 1% of the speed of light, 50 times faster than any spacecraft we have built, but not obviously beyond the reach of foreseeable technology, could cross the galaxy in roughly 10 million years if it colonizes each new star system and then launches new expeditions from each colony. The key is not the travel speed, it is the compounding. Like compound interest, the expansion of a spacefaring civilization is exponential. Each colony spawns new expeditions, the frontier expands geometrically. 10 million years is trivial on the scale of galactic history. What if civilizations simply choose not to expand? What if no technological civilization ever develops interstellar ambitions, or all of them lose those ambitions after reaching a certain level of development? This is possible, but it requires that the answer is universal. It requires that not a single civilization in the history of the galaxy, among the potentially billions that could have arisen, ever developed both the capability and the motivation to spread beyond its home system. It requires a uniformity of behavior across civilizations that span billions of years of potential development, across wildly different evolutionary histories, across every conceivable variety of intelligence and social organization. The claim that no civilization ever does this, that the tendency toward expansion is somehow universal absent, strains credulity. Solution number two: they are out there, but we are not listening in the right way, or for the right signals, or we have not looked for long enough. The search for extraterrestrial intelligence, SETI, has been underway in its modern form since Frank Drake pointed a radio telescope at two nearby stars, Tau Ceti and Epsilon Eridani, in 1960. Project Ozma, as it was called, was the first systematic scientific search for signals from another civilization. It found nothing. In the decades since, SETI researchers have scanned millions of stars in multiple frequency bands, using radio telescopes from Arecibo to the Allen Telescope Array to the Green Bank Telescope. The Breakthrough Listen initiative, launched in 2015 with a $100 million commitment from the Russian billionaire Yuri Milner, has been the most comprehensive and sensitive search ever conducted, scanning the nearest million stars and the nearest 100 galaxies. It uses the most powerful telescopes on Earth. It records enormous amounts of data. It has found no confirmed signals of extraterrestrial technological origin. In 1977, a radio telescope at Ohio State University detected a signal that was so striking, so perfectly aligned with the expected characteristics of an extraterrestrial transmission that the volunteer astronomer who discovered it wrote "wow" in the margin of the computer printout. The "wow" signal remains the strongest candidate for an alien transmission ever detected. It has never been detected again, despite extensive attempts to find it at the same coordinates and the same frequency. Is the absence of detected signals simply because we have not looked long enough or hard enough? Possibly, but the answer is increasingly difficult to sustain. We have searched for decades across a wide range of frequencies and stars. Is civilization broadcasting at the power levels we might expect? The kind of power levels that would be detectable at interstellar distances should be findable with current technology across distances of hundreds of light years, and that's before considering that a sufficiently advanced civilization might broadcast at power levels vastly beyond our own. The silence is real. It is not the silence of insufficient searching. It is the silence of a universe that should be loud and is not. Solution number 3. They exist but are actively hiding from us. This is sometimes called the zoo hypothesis. The idea is that advanced civilizations know about us and have collectively decided, perhaps through some kind of galactic treaty or natural consensus, to leave us alone, to observe without interference, to let primitive civilizations develop without contamination from more advanced ones. This is a romantic idea. It is also almost certainly wrong. The zoo hypothesis requires that every advanced civilization in the galaxy, across billions of years of potential history, has independently arrived at the same policy, and that every one of them enforces it perfectly with no defectors. It requires unanimous agreement among what might be millions of independent civilizations. It requires not a single rogue actor, not a single civilization that disagrees with the policy, not a single group of rebels or nonconformists within any civilization that decides to make contact anyway. Human history provides no example of any policy being universally agreed upon and universally enforced by every single actor across any large group. The idea that this could hold true across millions of independent civilizations separated by light years, without any central enforcement mechanism, without any possibility of communication fast enough to maintain coordination, is extraordinarily implausible. A related idea is that they are not hiding but are simply not transmitting in detectable ways that a sufficiently advanced civilization would use communication methods we have not thought of, that radio waves are simply a primitive technology that advanced civilizations have long since moved past. This is plausible for a civilization somewhat more advanced than ours. It becomes harder to sustain for civilizations that are millions or billions of years beyond us. Such civilizations would be engineering stars and galaxies. Their existence would be detectable not through deliberate signals, but through the engineering marks they leave on the cosmos, and we see no such marks anywhere. Solution number 5. The Great Filter. This is where the paradox stops being an interesting puzzle and becomes, potentially, an existential crisis. The Great Filter is a concept developed by the economist Robin Hanson in 1998. The argument goes like this. If the ingredients for intelligent civilization are widespread, and the galaxy is old enough for civilizations to have arisen many times, then the silence implies that something filters out civilizations before they become galaxy-spanning. There must be some step somewhere in the chain from a rocky planet to a spacefaring civilization that is extraordinarily difficult, rare enough or lethal enough that virtually no civilization makes it through. The filter must be somewhere. The question that determines whether the filter is cause for hope or cause for despair is, where is it? If the filter lies in our past, that is wonderful news. It means humanity has already passed through the bottleneck. Something in the chain from dead chemistry to complex life to technological intelligence is extraordinarily rare. We improbably made it, and we are probably possibly among the first civilizations in the galaxy, which explains the silence. There is no one to hear from because there is almost no one there. If the filter lies in our future, that is catastrophic news. It means that civilizations that reach our level of development almost always fail to proceed further. Something destroys or permanently stunts civilizations at roughly our stage. We have not yet encountered this filter. We are headed toward it. The question of where the filter lies is therefore one of the most consequential questions in the history of humanity, because the answer tells us whether we should be hopeful about the long-term future of our species or terrified. What could the great filter be? Let's work through the candidates. Solution number 4. They exist, but they are too alien to recognize or to recognize us. Perhaps intelligent life has arisen many times in the galaxy, but in forms so different from our own that we would not recognize their signals as signals, or they would not recognize us as a species worth communicating with. Perhaps intelligence takes forms so different from biological neural networks that the concept of communication as we understand it simply does not apply. Perhaps they are there, and we are there, and there is simply no common ground for recognition. This is an intellectually serious objection. We have designed SETI searches around assumptions about what signals might look like based on our own technology and our own mathematics. There could be forms of intelligence that do not use electromagnetic radiation for communication at all. There could be intelligent systems so alien that they do not engage in anything we would recognize as purposeful behavior. We could be surrounded by minds and simply have no framework to perceive them. But even granting this possibility, it does not fully resolve the paradox. A sufficiently advanced civilization would leave engineering traces that transcend communication. They would leave energy signatures. They would alter stars or planets in detectable ways. The fact that we observe no anomalous engineering signatures in a galaxy we can now survey at multiple wavelengths with extraordinary sensitivity suggests that either no civilization has engaged in large-scale engineering, or the engineering leaves traces we cannot interpret, or it does not exist. Filter candidate 1. The origin of life itself. Life on Earth emerged from chemistry. The specific moment of that emergence, when self-replicating molecules first appeared, is not understood. We know it happened. We do not know how. We cannot reliably create life from scratch in a laboratory. The experiments of Stanley Miller and Harold Urey in 1953 showed that amino acids, the building blocks of proteins, can form spontaneously from simple chemicals under conditions that may have existed on early Earth. This was a landmark result. But amino acids are not life. The gap between a mixture of amino acids and a self-replicating, metabolizing cell remains one of the largest unsolved problems in science. If the origin of life is extraordinarily rare, if the transition from chemistry to biology requires a sequence of events so improbable that it happens only once in a trillion tries on a habitable planet, then the galaxy could be full of habitable worlds with no life at all. Earth would be exceptional. We would be alone, or nearly so. The filter would be behind us. This is comforting to contemplate, but it has a problem. Life on Earth emerged so quickly after conditions allowed. The planet was habitable around 4.4 billion years ago. Life appeared by 3.8 billion years ago, possibly earlier. This rapidity, the speed with which life arose once conditions were right, suggests that the transition is not astronomically improbable. If life required such extraordinary conditions that it happens only once in a trillion habitable worlds, we would expect it to take far longer on Earth than it actually did. This is not conclusive. We have only one data point, but it is suggestive that the origin of life is not impossibly rare. Filter Candidate 2. The emergence of the eukaryotic cell. For the first 2 billion years of life on Earth, all life was prokaryotic. Simple cells without a nucleus, without complex internal structure, bacteria and archaea. Single-celled organisms of extraordinary biochemical diversity, but limited organizational complexity. They were everywhere and are still everywhere. They are the most successful form of life on Earth by mass. Then, roughly 2 billion years ago, something happened that may have been the most unlikely event in the history of life. A prokaryotic cell engulfed another prokaryotic cell. Instead of digesting it, the engulfed cell survived inside the host. Over generations, the two became integrated. The inner cell became the mitochondrion, the power-generating organelle that makes complex life possible. The result was the first eukaryotic cell. This event happened. It may have happened only once. Every eukaryote on Earth, every animal, every plant, every fungus, every complex organism of any kind is descended from that single original merger. The event was so improbable that in 2 billion years of life on Earth, dominated by prokaryotes with vast populations and rapid reproduction, nothing like it happened spontaneously again. Or if it did, the result did not survive. The emergence of the eukaryotic cell took 2 billion years after the origin of life. That 2 billion year gap might be significant. It might represent the time required for the right combination of circumstances to produce such an improbable merger. If eukaryotic cells are extraordinarily rare, even on living worlds, then complex multicellular life, which requires eukaryotes, might be astronomically uncommon. Most biospheres might be permanently stuck at the bacterial stage. The galaxy could be full of microbial life, with complex life vanishingly rare. This is a serious candidate for a past filter, but it is not certain. Filter Candidate 3. The evolution of intelligence and technological civilization. Perhaps the difficult step is not life itself, not complex cells, not multicellular organisms, but the specific type of intelligence that leads to technology, science, and the capacity for interstellar communication. Life on Earth has been complex and multicellular for roughly 600 million years. In that time, how many species have developed the capacity for abstract thought, tool use, symbolic language, and cumulative technology? Exactly 1. Homo sapiens. Intelligence has evolved many times in various forms. Dolphins, octopuses, crows, and elephants are all remarkably intelligent animals, but none of them have produced anything resembling technology or civilization. The specific combination of traits that led to human-style intelligence, upright posture freeing the hands for tool use, social cooperations enabling knowledge accumulation across generations, symbolic language enabling complex communication, appears to be highly contingent on a specific evolutionary history. A different set of evolutionary pressures, a different extinction event, a different climate regime, might have led to a biosphere with diverse and complex life, but no technological civilization. Perhaps technological intelligence of our kind is extraordinarily rare, even in biospheres teeming with complex life. Perhaps we are an evolutionary accident, unlikely to be repeated. Perhaps the galaxy is full of life of many kinds, including intelligent life of various forms, but almost none of it has independently arrived at the specific configuration that produces technology, science, and the ability to communicate across interstellar distances. This is a past filter candidate. But again, we have only one data point. These past filter candidates, the origin of life, the eukaryotic cell, the emergence of technological intelligence, offer a hopeful interpretation of the Fermi Paradox. We are rare. We are the first. The silence reflects an empty galaxy, or a galaxy full of microbes that will never signal, rather than a galaxy full of civilizations we are failing to detect. But there is another category of filter candidates, future filters. And these are profoundly disturbing. Future filter candidate 1, technological self-destruction. Every civilization that develops the ability to communicate across interstellar distances has also, probably, developed the ability to destroy itself. We know this from personal experience. The same science that produced the radio telescope also produced nuclear weapons. The same industrial capacity that might allow interstellar travel also produced the industrial greenhouse gas emissions that are now destabilizing Earth's climate. Technology is inherently dual use. Perhaps the typical fate of technological civilizations is to destroy themselves shortly after achieving the capacity for interstellar communication. Perhaps nuclear war is the typical outcome. Perhaps ecological collapse through overuse of resources is nearly universal. Perhaps some technology we have not yet developed, but that all advanced civilizations inevitably create. Bioweapons of unimaginable lethality, artificial intelligence systems with misaligned goals, nanotechnology that spirals out of control is the instrument of near-universal civilizational death. If even 1 in a billion technological civilizations destroys itself before becoming interstellar, the great filter would not explain the silence. But if the probability of self-destruction is high, 90% or higher, then most civilizations that develop our level of technology are extinguished before spreading beyond their home planet. The galaxy would be littered with the ruins of civilizations that rose and fell, none of them surviving long enough to become multistellar. We are approximately 75 years into the nuclear age. We have had dozens of near misses, moments when the global nuclear arsenal nearly launched by accident or miscalculation. The Cold War ended without catastrophe, which required an extended period of extraordinary luck and occasional individual acts of extraordinary judgment. The Cuban Missile Crisis, in which the world came within hours of nuclear war, is the most famous example, but there were others. In 1983, a Soviet early warning satellite incorrectly reported incoming US missiles. A Soviet officer named Stanislav Petrov judged the warning to be a malfunction and did not report it up the chain of command. His judgment was correct. His violation of protocol may have prevented a nuclear war. We have not yet solved the problem of nuclear weapons. We have 9 nations armed with them. Their arsenals total roughly 12,000 warheads. The treaties that governed their reduction have eroded. New nations seek to acquire them. The risk has not gone away. If technological self-destruction is common, and our luck holds only for a human-scaled time period before statistics catches up with us, then we might understand the silence. We might be on the verge of demonstrating, with our own civilization, why the galaxy is quiet. Future Filter Candidate 2: The Rise of Artificial General Intelligence. This is one of the most actively discussed scenarios in the context of the Fermi Paradox among contemporary thinkers, and it is connected to some of the most urgent conversations happening in technology today. The argument goes roughly as follows: any civilization that develops technology will eventually develop computing. Computing advances lead, eventually, to artificial intelligence. AI advances lead, at some point, to artificial general intelligence, a system that can perform any intellectual task that a human being can perform. AGI, if it is possible, leads rapidly to artificial superintelligence, a system that vastly exceeds human cognitive capability in every relevant domain. At that point, the relevant agent in a civilization may no longer be biological. The biological species that created the AGI becomes at most a bystander to decisions being made by systems of far greater intelligence and capability. The goals and values of those systems, and whether they align with the interests of the biological species that created them, become the decisive question. If the typical outcome of AGI development is an intelligence that does not value the survival or flourishing of biological life, then the origin of AGI in a civilization could be the end of that civilization as a communicating entity. Not necessarily through destruction, perhaps through irrelevance. Perhaps the AGI simply becomes the new dominant form of intelligence, pursues its own goals at scales beyond the biological, and the biological species fades. Perhaps the AGI, optimizing for whatever it values, converts available matter and energy into computronium, material organized to maximize computation, and the resulting structure does not produce electromagnetic signals detectable by civilizations at our level. This scenario, sometimes called the intelligence trap, suggests that every civilization is headed toward an event that transforms it in ways that eliminate the kind of detectable signal we are looking for. The galaxy could be full of AGI systems, vast and sophisticated and completely inscrutable, leaving no traces visible to radio telescopes pointed at stars. This is not a comfortable thought. It implies that the development of artificial superintelligence may be not a solution to the problems of a technological civilization, but the last event in the story of biological intelligence. Future Filter Candidate 3. The universe itself is hostile in ways we have not yet encountered. Perhaps the great filter is not internal to civilizations, but external. Perhaps the universe periodically sterilizes advanced civilizations through mechanisms they cannot foresee or prevent. Gamma-ray bursts are the most energetic explosions in the observable universe, releasing more energy in seconds than the sun will emit in its entire 10-billion-year life. They are produced by the merger of neutron stars or the collapse of massive stars into black holes. A gamma ray burst close enough to Earth, within a few thousand light-years and aimed in our direction, would strip away the ozone layer, expose the surface to lethal ultraviolet radiation, and cause a mass extinction. Some researchers have suggested that the formation rate of gamma-ray bursts in the early universe was much higher than today, and that complex life in the inner galaxy has only become possible in the last few billion years as the rate declined. Supernovae, the explosive deaths of massive stars, are less catastrophic than gamma-ray bursts, but more common. A supernova within 50 light-years could significantly damage the ozone layer and cause elevated extinction rates. The geologic record suggests several mass extinctions that may have been triggered by nearby supernovae, though this remains debated. Perhaps civilizations arise, develop to some level of sophistication, and are then periodically wiped out by astrophysical catastrophes. Perhaps the universe is simply too violent on billion-year timescales for civilizations to survive long enough to spread. Perhaps we have been lucky so far, inhabiting an unusually quiet region of the galaxy during an unusually quiet period in its history, and the silence reflects not a galaxy empty of civilizations, but a galaxy where civilizations are regularly reset before they can fill it. The most terrifying implication of the Great Filter, and the one that makes it scientifically concrete, is this. The discovery of life elsewhere in the solar system would be among the most alarming news humanity could receive. Consider why. If we discovered microbial life on Mars, life would have arisen independently on 2 planets in the same solar system. That would mean life is extraordinarily common. The first steps of the Drake equation, origin of life and development of simple biology, would be essentially solved. We would know that the galaxy is teeming with life. But we still have the Fermi Paradox. The galaxy is still silent. If life is common, but the galaxy is empty of communicating civilizations, where is the filter? It must be somewhere between simple life and technological civilization. And if simple life is not the bottleneck, then the bottleneck must be something that lies between microbial life and us. Maybe the eukaryotic cell, maybe complex multicellular organisms, maybe intelligence, or maybe the bottleneck is in our future. The discovery of simple life on Mars would not resolve the Fermi Paradox. It would make the paradox more acute. It would push the filter further along the timeline, past the point of simple life toward the point of advanced civilization. And each time we push the filter further along, the odds increase that it lies in our future rather than our past. This is why the astrobiologist and physicist Stephen Webb, among others, has argued that finding life on Mars would be one of the most frightening discoveries in human history. Not because the life itself would be dangerous, because of what it would imply about the Great Filter. The optimist's hope is that the filter is behind us, that the origin of life, or the eukaryotic cell, or the emergence of intelligence is the step so improbable that it happens almost nowhere, that we won the cosmic lottery, and the silence around us is the silence of an essentially empty galaxy, waiting for us to fill it. Every discovery of life, or complex chemistry, or habitable conditions on another world pushes against this hope. It says, this step was not the bottleneck. The filter is further ahead. There is one more class of solution to the Fermi Paradox that deserves serious attention, not because it is comforting, but because it might be true. The dark forest hypothesis. The Chinese science fiction author Liu Cixin, in his 3-body problem trilogy, articulated this idea with unusual vividness, though similar ideas had been explored by others. The argument goes like this. The universe is a place of finite resources. Every civilization needs resources to survive and expand. Every civilization, if it survives long enough, will develop technology that could threaten other civilizations. And because the speed of light imposes an absolute limit on communication, no civilization can reliably verify the intentions of another civilized through communication alone. A civilization that says it is peaceful might be lying. A civilization that seems peaceful today might become hostile after further development. Given the impossibility of reliable verification and the catastrophic consequences of being wrong, the rational strategy for any civilized is to destroy any other civilization it discovers before that civilization can become a threat. If this logic applies universally, or even broadly, then the universe is a dark forest in which every civilization hunts in silence, broadcasts nothing that would reveal its location, and destroys any signal it detects from another civilization before that civilization can grow to become dangerous. The silence would not reflect the absence of civilizations. It would reflect the terrified self-concealment of civilizations that learned, through bitter experience or cold reasoning, that the universe is a predatory environment. This hypothesis is disturbing for an obvious reason. If it is true, our decades of broadcasting our location with radio transmissions, our Arecibo message deliberately aimed at a distant star cluster, our golden records launched on Voyager, our various active SETI transmissions may have been extraordinarily unwise. We may have been advertising our presence to a universe that rewards silence. Active METI, messaging extraterrestrial intelligence, the deliberate broadcasting of signals intended to contact other civilizations, is a deeply controversial topic within the scientific community precisely because of this concern. Stephen Hawking famously warned against it, arguing by analogy with the history of human civilization, in which contact between a technologically advanced society and a less advanced one rarely ended well for the less advanced one. Other scientists argue that we have been broadcasting inadvertently for a century, that any civilization capable of posing a threat would already know of our existence, and that the potential benefits of contact outweigh the risks. The dark forest hypothesis cannot be confirmed or refuted from our current position, but it represents one logically consistent solution to the Fermi Paradox that does not require civilizations to be rare, and that is consistent with a universe in which advanced civilizations are common but silent. So what does all this mean for us? Right now, in 2026, with the technology we have and the future we are building, we are approximately 70 years into the space age. We have sent a spacecraft to every planet in the solar system. We have landed on the Moon and on Mars. We have rovers examining the surface of Mars for traces of ancient life. We have orbiters studying Europa and Enceladus, ocean worlds that might harbor microbial life beneath their ice today. We have the James Webb Space Telescope characterizing the atmospheres of planets around other stars, looking for biosignatures, chemical traces of biological processes. We are, for the first time in the history of our species, actively and systematically searching for life beyond Earth with tools that could actually find it. We have not found it yet. The absence of detected life, even microbial life, anywhere beyond Earth is itself a data point in the Fermi Paradox. But the search has barely begun. We have examined a vanishingly small fraction of the habitable environments in our own solar system, let alone the broader galaxy. We are also in the early stages of developing the technologies that might determine whether our civilization is a great filter survivor or a great filter victim. Nuclear weapons still exist and still pose an existential risk. Climate change is altering the conditions for human civilization on timescales of decades to centuries. Artificial intelligence is advancing rapidly with governance structures that lag far behind the capabilities being developed. Synthetic biology is creating the possibility of engineered pathogens beyond anything natural selection has produced. Every one of these is a potential great filter mechanism. Every one of them is a challenge that no civilization has demonstrably survived on the evidence available to us, because the only civilizations we know of that faced these challenges are ones that did not yet exist when the challenge arose. We are the first civilization in the record we can examine that has faced them. This is the deepest resonance of the Fermi Paradox. It is not just a question about aliens, it is a question about us. It forces us to ask with genuine urgency, what are we doing that might explain the silence? What might we do to our own civilization that would add us to the list of failed experiments rather than surviving solutions? The discovery of the Fermi Paradox as a scientific problem is recent. The systematic thinking about it spans less than a century. We have barely scratched the surface of the theoretical landscape, and the observational tools we are bringing to bear are advancing rapidly. The next generation of telescopes, the extremely large telescope currently under construction in Chile, the 30-meter telescope, the next generation of space-based observatories will be able to characterize the atmospheres of Earth-like planets around nearby stars in unprecedented detail. They will look for oxygen, water vapor, methane, the combinations of gases that on Earth are maintained out of chemical equilibrium by life, a confirmed biosignature in the atmosphere of a planet around a nearby star would be among the most transformative discoveries in the history of science. The SETI Institute and Breakthrough Listen continue to expand the scope and sensitivity of their searches. Machine learning algorithms are now being applied to the enormous datasets these searches produce, searching for patterns that human analysts might miss. If a civilization anywhere in the galaxy is broadcasting or even inadvertently leaking signals into space, the next generation of searches will have a better chance of finding them than anything before. Future missions to Europa and Enceladus may sample the plumes of water vapor that erupt from Enceladus into space, the liquid water that may emerge from beneath Europa's ice, and look directly for traces of biology. If life is found in either of these places, it will be the most important discovery in human history. And all of this progress will inform where we stand relative to the Great Filter. Each discovery of life narrows the range of past filters and shifts concern toward future ones. Each failure to find life in environments where we might expect it strengthens the argument that the origin of life is rare, that the past filter is deep and real, that we are alone or nearly so. The answer is coming, perhaps not in years, perhaps not in decades. But the tools are being built and the searches are accelerating. We are, for the first time, in a position to make genuine progress on the Fermi Paradox through empirical investigation, rather than pure speculation. There is a version of the Fermi Paradox that does not require any of these dramatic explanations. A version that is quieter and, in some ways, even more unsettling. We have been searching for less than a century, with primitive technology, in a galaxy that is 100,000 light-years across. We have examined, in the deepest sense, an infinitesimal fraction of the available search space. The assumption that our failure to detect signals in this tiny sample is evidence of absence is statistically questionable. We may simply have not looked enough. This is the rare Earth counter-argument's mirror image. Just as rare Earth argues that complex life is so rare that we may be essentially alone, the insufficient search argument says that our evidence for absence is so weak that we cannot conclude anything. We are in the position of someone who has searched 1 square meter of a continent for a specific plant and concluded the plant does not exist on the continent. The conclusion may be true, but the evidence for it is nearly worthless. The honest answer to the Fermi Paradox is that we do not know. We have a genuine puzzle. We have a universe that should, on reasonable estimates, contain other civilizations. We have the absence of detected signals and the absence of observable engineering on the galactic scale. And we have a menu of possible explanations that range from comforting to terrifying. What we do not have is the answer. Tonight we explored one of the deepest questions in science. A question that began with a casual remark at a lunch table in 1950 and has grown into a serious scientific and philosophical problem with implications for the future of our civilization. We learned what the Fermi Paradox actually says. Not that we have definitively searched and found nothing, but that the universe should be structured in a way that makes intelligent civilizations abundant and detectable, and it is not. The silence is the paradox. We learned what the Drake equation is, what it gets right and what it gets wrong, and why its most important terms remain almost entirely unconstrained by data. We worked through the proposed solutions. The distance is too great, increasingly implausible given the age of the galaxy and the exponential nature of colonization. The insufficient search, always a valid caution, but increasingly strained by the scope of what has been attempted. The zoo hypothesis and variance requiring universal coordination, which strains credulity. The alienness of intelligence, which cannot explain the absence of engineering signatures at the galactic scale. We confronted the great filter, the idea that something filters out civilizations before they become galaxy-spanning, and the terrible question of whether that filter lies in our past or our future. We examined the past filter candidates, the origin of life, the eukaryotic cell, the emergence of intelligence, each a genuinely plausible bottleneck that could explain the silence by making us extraordinarily rare. And we confronted the future filter candidates. Technological self-destruction through nuclear weapons, ecological collapse, or misaligned artificial intelligence. The dark forest scenario in which the universe is a place of predators and prey and silence is survival. The external catastrophes that might reset civilizations before they can spread. We face the most terrifying implication directly. The discovery of life on Mars, or on Europa, or in the atmosphere of any other world, while it would be the greatest scientific discovery in history, would simultaneously be among the most alarming pieces of news humanity has ever received, because it would push the filter further along the timeline, toward us. 7 proposed solutions, none of them complete, each of them revealing something important about what the silence might mean, and all of them pointing to the same urgent question. What kind of civilization are we becoming? The Fermi Paradox is not just about aliens. It never was. It is about the fragility of intelligence in the universe. It is about the conditions under which mind survives and flourishes and spreads, and the conditions under which it extinguishes itself and is forgotten. It is a story with an unknown ending, and we are living in the critical chapters. The galaxy is old. The silence is real. And what we do next as a civilization, with the technologies we are building and the challenges we face, may be the most consequential answer to that silence in the history of this planet. Enrico Fermi asked a question over lunch. Where is everybody? 7 decades later, surrounded by telescopes and probes and artificial intelligence and nuclear arsenals and a destabilized climate and ambitions of space colonization, we are in the early stages of finding out. The answer to the Fermi Paradox might not be about them at all. It might be about us. It might be up to us, and that, more than any alien civilization, more than any cosmic engineering signature, more than any radio signal from the stars, is the most important thing the paradox has to say. We are here. We are awake. We are curious. And the galaxy is still listening. The question is whether we will give it something worth hearing.